Hello again, and welcome back to another episode of the CCQTA Lunch and Learn series. I'm Dave Murray, Secretary of the CCQTA and Principal Consultant at Omnicon Consultants. This is our first episode on chlorides in crude oil. In this episode, we're going to focus on the following. First, I'll describe the two types of chlorides, how each type travels through the refinery, and what impact each type can have on refinery equipment. Then we'll look at the sources for both organic and inorganic chlorides and how these materials end up in crude streams. Next, we'll review the test methods used to measure both types of chlorides and discuss some of the challenges and nuances with applying and interpreting those results. And lastly, we'll discuss some industry experiences which demonstrate how the lines between organic and inorganic chlorides can often be blurred. Let's start with inorganic chlorides. Sodium chloride, magnesium chloride, and calcium chloride are common salts present in crude oil production. Their concentration in crude can range from low parts per million to levels in excess of 1,000 parts per million. The concentration is mostly dependent on the type and location of the production. These chloride salts are shown here in the ionic form to illustrate the electron sharing between the atoms. On their own, they're solid crystalline salts, think of like table salt. However, since the salts are soluble and ionizable, when they're introduced into the water, the polarity of the water causes the two ions to dissociate from one another into positive and negative ions within the solution. As you might imagine, since salts can't be turned into gasoline or diesel fuel, etc., they're identified as a contaminant in crude oil. Typically, plant fouling and corrosion are the key processing issues attributed to salt. Therefore, the salts must be removed in a process called desalting. In the refinery desalter, the incoming crude is mixed with fresh water, usually at about 6% by volume. This water contacts the salts present in the crude, causing them to dissolve into the water, which is then separated from the crude primarily by density differences. The desalted crude then proceeds to the crude unit, while the salt-rich water is sent to the wastewater treatment plant. In most refineries, desalting efficiencies are in the range of about 95% or greater, and the resulting salt levels in the desalted crude are typically in the 1 to 10 ppm range. This significantly reduces the amount of salt carried further into the refining process and alleviates the downstream corrosion issues due to salt hydrolysis in the primary distillation column. Since I mentioned it, let's discuss salt hydrolysis a little further. Residual salts left in the crude after desalting will undergo hydrolysis due to steam addition in the crude unit flash zone, where temperatures can range from 315 to 370 degrees C or 600 to 700 degrees Fahrenheit. At these temperatures, in the presence of steam, the chloride dissociates and combines with hydrogen to form hydrogen chloride vapor, which travels up the tower where it's absorbed by the condensing steam, forming liquid hydrochloric acid. Initial dew point pHs of the condensed water phase can often drop below 4.5 and lead to corrosion of overhead equipment. Historically, ammonia has been injected into the tower overhead to help neutralize the acid. However, since ammonium chloride forms fouling or corrosive deposits, most crude units now employ proprietary non-fouling neutralizers to manage corrosion, and we'll look at those issues a little further later on. Inorganic salt hydrolysis rates are determined by the type of chlorides in the crude. Magnesium chloride is more hydrolyzable than calcium chloride, and sodium chloride has the lowest hydrolysis rate. HCl formation in the crude unit feed is managed by salt removal in the desalter and also by the addition of caustic into the desalted crude. Caustic helps reduce and neutralize hydrochloric acid generation by forcing the reversible reaction to keep the chloride in the sodium chloride state. Now that we've reviewed inorganic chlorides, let's have a look at organic chlorides. These are a few examples of organic chloride structures. The two on the left are referred to as alkyl chlorides because of the carbon chain attached to the chlorine. The alkyl chain can be any length from one carbon to many. The chain length is really dictated by the manufacturer for its fit for purpose. Methylene chloride, for example, is a very effective degreaser for many applications. In the past, however, when used as a cleaning fluid in the oil field, it has often inadvertently been disposed of in oil sumps, which are then injected into pipelines and find their ways to refineries. The example on the right is the more complex structure of tetrachloroethylene, which is used as brake cleaner and/or dry cleaning fluid. In the case of brake cleaner, it may enter the crude system in the same manner as methylene chloride if used for degreasing. Unlike inorganic chlorides, organic chlorides are not water-soluble, so refiners are unable to remove them from the crude during the desalting process. The organic chlorides are carried with the crude through the desalter and into the process. Organic chlorides, when present in the crude, are typically in the 1 to 10 ppm range. Organic chlorides will travel through the desalter and the atmospheric crude unit and then accumulate in the crude overhead naphtha. The light virgin naphtha containing organic chlorides then moves to the naphtha hydrofiner. The naphtha hydrofiner or hydrotreater is a catalyzed reactor unit with hydrogen addition used to remove both sulfur and nitrogen prior to using the naphtha as reformer feed. When the organic chlorides reach the hydrofiner, the reactor catalyst coupled with added hydrogen breaks the alkyl chloride bond and produces HCl. The hydrotreated naphtha is then routed to a high-pressure separator where the fractions are separated. The lighter fraction condense in the coolers and exchangers along with any HCl and the small volumes of water produced from the reactor. These conditions favor the concentration of HCl and the development of very low pH and extremely corrosive environments. Another product of the hydrofiner reaction is the formation of ammonia, which is a byproduct of the denitrification of the naphtha. Ammonia reacts with HCl to form ammonium chloride. As a result, significant downstream exchanger fouling due to ammonium chloride salt deposition can occur within the hydrofiner feed effluent exchangers. For many refiners, fouling of these exchangers is often the first indicator of the presence of organic chlorides in the crude unit feed. Where do chlorides come from? The inorganic salts are native to crude oil because they are produced with the oil in the reservoir. Crude oil is formed from the remains of dead organisms such as algae and zooplankton that existed millions of years ago in a marine environment. The marine environment contains salt water which exists in the same reservoir as the oil. By comparison, organic chlorides are considered non-native to crude oil and assumed to be the result of contamination during production or transportation. Known sources of contamination include waste oils, cleaning solvents, and dry cleaning fluids. It is also worth noting at this point that certain crude oil production processes, such as acidizing, fracturing, and unconventional production techniques, can also lead to organic chloride formation, which then does challenge the assumption that organic chlorides are not native to crude oil. Let's start with inorganic chlorides. As a general rule, inorganic salts are dissolved within small volumes of produced water present within the crude oil, although some solid crystalline salts can also be carried with the crude as an inorganic solid. In some cases, these solid crystalline salts can also become coated with heavy organics such as asphaltenes. These coated salts are insoluble in water, therefore they cannot be readily removed during the desalting process. These have been aptly nicknamed Smarties. Smarties will make their way to crude distillation tower where the asphaltene coating is removed in the flash zone, allowing the residual salt to undergo hydrolysis like we talked about earlier. One application where Smarties can be inadvertently produced is when heavy crude is exposed to severe flash evaporation during surface treating. In this case, the salt-rich water is boiled away, concentrating the salts until they precipitate, leaving solid crystalline salts behind in the crude. As the oil is dried, the salts contact the asphaltenes to form Smarties. This is one of those scenarios where a production practice can unknowingly but significantly impact refining. As we talked about earlier, chlorinated solvents such as dry cleaning fluids and waste oils are common sources of organic chlorides, and their occasional appearance in crude oil has been well documented. There have been several incidents in the past where contaminated crudes have been linked to either intentional or inadvertent disposal of these materials in crude oil. Industry is now generally cognizant of these materials as contaminants, and these events are now relatively rare. What is less understood, however, is the role of production practices such as acidizing and hydraulic fracturing on organic chloride formation. Anytime a concentrated solution of hydrochloric acid is injected downhole in conjunction with alcohols, olefinic materials, or polar solvents, the risk of chlorinating some hydrocarbons exists. This example shows the reaction of 2-propanol with hydrochloric acid to form 2-chloropropane and water. Organic chloride levels up to 25 ppm can be expected during certain well stimulation activities. Therefore, a treated well should be flowed back to tankage after treatment for special handling in order to minimize organic chloride contamination of the produced crude. In the past, oil-based well fracturing normally employed dialkyl phosphate esters as the active ingredient in the frac gellant. This illustration is an example of dialkyl phosphate ester. Note the 2 hydrocarbon chains of different lengths. These are adjusted by the chemical manufacturer to achieve the required gellant properties. As previously discussed within the CCQTA's phosphorus and crude project, this particular additive has been connected to phosphorus-related fouling in the refinery crude towers, specifically in the jet and diesel draw areas. This fouling material reduced the diameter of the tray holes, limiting throughput, allowing trays to flood. This is another example of phosphorus-related fouling being scraped off the walls of the tower. Additional work completed by the CCQTA on the phosphorus fouling issue has also determined that some of these volatile esters in the crude tower can react with hydrochloric acid to form organic chlorides. As we talked about earlier, the acid is already present in the tower due to inorganic salt hydrolysis. It then reacts with the phosphate ester group to form an organic chloride. Finally, while there's been limited reported evidence of organic chloride formation linked to crude production techniques, there is one known case. In 2017, the CCQTA reported on the formation of a chlorinated benzene compound in a facility using toe-to-heel air injection, or the TIE process, for oil production. This process injects air into the reservoir to allow ignition of the oil at the toe, which in turn warms the reservoir, reducing the bitumen viscosity so that it can be produced at the heel. This organic chloride formation case is believed to be due to the unusually aggressive combustion conditions involved in the process and remains the only reported case of organic chloride formation during production. Now that we know what the problems associated with the different types of chlorides are, let's look at the methods used to detect them. There are three established ASTM methods for measuring chlorides in crude oil. D3230 and D6470 are for inorganic chlorides, and D4929 is for organic chlorides. I will also mention ASTM D7536 because it does get used, however it is intended specifically for aromatics and not for crude oil. D3230 correlates the conductivity of the crude oil to the salt content of reference standards. D6470 extracts the soluble inorganic salts from the crude oil into water, and then the extract water is coulometrically titrated for the chloride content. D4929 involves a two-step process that I'll describe in more detail in a minute. First, let's talk about some nuances of the inorganic chloride methods that should be understood. D3230 has been used extensively in the past, however there are numerous potentially interfering conductive components within crude oil which can bias results, so this method has lost its appeal for many users. D6470 requires that all the inorganic chlorides in the oil sample be dissolved in a water-based solvent prior to titration. This requirement for complete extraction of the salt from the oil matrix can be challenging and has led to the development of modified steps, such as refluxing samples in a toluene water mixture, the Crude method, and or employing microwave energy to improve water-salt dissolution. Now let's look at the more complicated D4929 method. D4929 involves a two-step process. Firstly, an ASTM D86 type distillation is carried out to isolate a naphtha fraction with the distillation stopped at 204 degrees C. This fraction is then washed with caustic to remove hydrogen sulfide and then repeatedly washed with deionized water to remove the soluble inorganic chlorides. Any remaining chlorides in the naphtha are considered hydrocarbon-soluble organic chlorides. Second, the washed naphtha fraction is analyzed by one of three different procedures. Procedure A involves reacting the organic chlorides with sodium biphenyl, which converts the organic chloride to an inorganic chloride, and then the separated aqueous phase is titrated potentiometrically for chloride. Procedure B uses high temperature oxidative combustion of the organic chlorides prior to the coulometric titration. Procedure C uses X-ray fluorescence spectroscopy to detect and quantify the chlorides in the naphtha. UOP has also published two methods for measuring organic chlorides, UOP 588, which is similar to D4929A, and UOP 779, which resembles D4929B. The D4929 method has some very specific nuances you should be aware of. The preparation procedure in D4929 requires that a distillation be performed to isolate the naphtha cut at 204 degrees C. The D4929 method calls for a 500 ml sample size for distillation to ensure sufficient naphtha is available for analysis by one of the three procedures. However, many labs will use a faster D86 distillation, which only uses 100 ml sample volume. In most cases, this doesn't cause any problems with the subsequent analysis. However, in some situations where there is a limited amount of naphtha available, say less than 7 or 8%, issues have been reported. For samples with low naphtha contents, like heavy oils, the naphtha isolation can be challenging, particularly if an automated distillation is used. For an automated D86 distillation unit to maintain the 4 to 5 ml per minute distillation rate prescribed by the method, it will continue to increase the heater temperature to drive more vapor into the condenser. By doing so, it also increases the flask surface temperature, and with the limited amount of thermal mass available, that can have unforeseen consequences. Hydrocarbon decomposition can occur, leading to the formation of reactive olefins. If salt hydrolysis also occurs as well, then the generated hydrochloric acid can then react with the olefins to form organic chlorides. This situation is aggravated by the presence of naphthenic acids in heavier crudes, since these are known to promote salt hydrolysis by as much as 30 times. Considering many heavy oils also have high TAN, then there is a high likelihood of this scenario. As mentioned earlier, dialkyl phosphate esters can react with HCl to form organic chlorides during distillation. As a result, when crude samples are provided for D4929 testing, sample owners have encouraged laboratories to undertake multiple water washes of the raw crude, and not the naphtha, in order to remove inorganic salt prior to distillation. They have argued that since refiners desalt all crudes, then any organic chlorides produced during testing should be treated as an artifact. The CCQTA has countered that, while desalting does remove most of the salt, it does not remove all of the salt. Residual salt will create HCl in almost all crude units and lead to organic chloride formation within the tower when trace levels of alkyl phosphate esters are present. The CCQTA has also published and posted a document on this subject on its website and has successfully lobbied ASTM to include text within D4929 discouraging this practice. This text has been included in the appendix section of D4929-17. Recently, the CCQTA was introduced to a promising method that is currently in development. This is a gas chromatography method utilizing a direct injection of crude oil and detection by the halogen-specific OI analytical XSD detector. The advantage of this method over ASTM D4929 is the elimination of the distillation and washing steps to prepare naphtha for analysis. This is a significant improvement in both the time of analysis as well as the method detection limit. The method also provides species information, which may prove invaluable to determine the source of contamination. In case you're wondering, inorganic salts will not be vaporized in the injector, so they will not impact the organic chloride analysis. Now, the method is still currently in development, but the CCQTA is working with Initech Alberta to provide real-world samples to assist in verifying the method. We'll be keeping a close eye on this one. Now let's look at some of the experiences reported in the industry. Because organic chlorides are so problematic for refiners and shippers, pipelines have instituted product quality specifications. These range from less than 1 ppm in the crude, which is also the method detection limit, to less than 1 weight ppm in the naphtha fraction, and then to the most stringent of must not contain any. These different specifications often lead to some confusion in the industry because a positive result usually leads to production being quarantined and producers potentially locked out from pipeline access. Every producer therefore hopes to have any tested sample reported as non-detect or ND, and this often leads to samples being retested at more than one laboratory, seeking the required result. It's not as nefarious as it sounds. The specifications are also at or below the method detection limit, where the reproducibility is highest, so the plus and minus could make the difference between meeting or exceeding the spec. Also, given the limitations of the method with null naphtha contents, there is potential for false positives, so asking another lab for a second opinion is not entirely unwarranted. Now, because positive results are rare, most labs are very careful when they do see a positive result and typically repeat the analysis using additional sample volume or verify both via other means. To give you an idea of the variation, in the mid-2000s, the CCQTA undertook a small round-robin testing for organic chlorides. In this case, 5 samples of D86 prepared naphtha, not the raw crude, were sent to 4 separate commercial laboratories for testing. Both D4929, procedures A and B, and D7536 methods were employed. Results revealed scatter in the data, which compelled the association to request that test facilities report samples without organic chlorides as less than the laboratory test method quantitation limit, and not as ND. You can see the organic chlorides letter to laboratories on the CCQTA website. In the early 1990s, a situation arose in a heavy crude where the measured salt content at the refineries was consistently higher than the levels reported at the production site, despite the fact that all locations employed the same conductivity test method. One of the receipt refineries was also experiencing severe crude unit corrosion problems. At that time, various theories proposing pipeline cross-contamination and/or the presence of organic chlorides were offered to explain the anomalies and plant corrosion problems. A detailed investigation determined that slop treatment practices at the production site involved the use of a flash evaporator like we talked about earlier. These oil-coated solids, or Smarties, were effectively undetectable at the source and only partially reported at the delivery point. These samples were collected and tested following thousands of kilometers of turbulent pipeline flow and the shearing action in pump stations. As a result, some of the crystalline salt was dissolved during transport. Subsequent test method verification involving laboratory-prepared samples spiked with crystalline salt determined that very little of the spiked salt was detected at all participating facilities. The test sample matrix shipped to all plant laboratories involved pre- and post-spike samples of the neat heavy crude. To alleviate this type of detection problem with crystalline salt, in the lab, heavy crude is often refluxed with toluene and water as part of sample preparation. This ensures the dissolution of the asphaltene shell, releasing the organic salts into the water for subsequent measurement of the inorganic chlorides. Alternatively, to verify the possibility of Smarties within a crude sample, the oil can also be tested for filterable solids first, as per ASTM D4807, and then the hot toluene wash solids can be scanned by XRD for the presence of crystalline salt. Let's change direction a little bit and talk about the postulated theory of organic chloride hydrolysis mentioned earlier. Since the early 2000s, a number of authors have proposed a link between the presence of organic chlorides in crude and crude unit corrosion. The chloride source in several reported case histories has been postulated as hydrolyzable organic chlorides. While there are several references to potentially hydrolyzable organic chlorides within the literature, for example dichloromethane, none of these hydrolyzable organic chlorides have been identified or directly measured within the crude oil in the reported case histories. In these case histories, the correlation between organic chlorides in crude and crude unit corrosion is generally done by inference or by difference, meaning chloride levels in the crude unit overhead boot water are too high for the measured salt content in the crude alone, and so then the difference must come from organic chlorides within the crude oil. Now, our goal here is not to contest the claim of hydrolyzable chlorides, but rather to provide some cautionary notes. All these experiences lead to some cautionary notes when interpreting chloride data. As we've shown here today, inorganic and organic chloride measurements in a crude oil matrix is difficult and it does have some pitfalls. D4929 may produce false positives under the right conditions, especially when the naphtha content is very low. Consider that a false negative is very unlikely because of the manner of detection. So if one lab is getting a positive result and another is getting a negative, the negative is likely to be correct. Not that you shouldn't do your due diligence and verify any positive result. Next, inorganic chlorides in crude oil can be very difficult to measure by traditional methods and do require the salts to be soluble in water. Like we've talked about, asphaltene-coated salt crystals like Smarties are resistant to water extraction, so they're likely not going to be detected. Also, differential XRF analysis of a pre- and post-water wash crude assumes that all inorganic chlorides are removed by the water and that those detected by XRF are organic, which may or may not be true, as we've discussed, how chlorides can be masked by other factors, so identification by inference should be taken with a grain of salt. Pun intended. Next, models employed to calculate crude distillation unit overhead chlorides from measured desalted crude salt content have limitations. Any attempt to model or project chloride content in crude overhead naphtha from desalted crude salt numbers does so by making a number of assumptions regarding variables, such as the distribution of the various salts, percent sodium, calcium, magnesium chlorides, the compositional impact on salt hydrolysis of the reused process waters as desalter wash water, the impact of crude oil naphthenic acid content on increasing salt hydrolysis, which some authors suggest the increase can be up to 30 times. Also, the effectiveness of the addition of caustic and or some metal oxides on inhibiting salt hydrolysis. Therefore, such modeling can be very difficult to correlate to real-world results. And lastly, specific hydrolyzable organic chloride molecules have not been actually identified directly in crude oils at this point. Given that inorganic salt hydrolysis is a well-understood phenomenon in crude towers, it seems like the more likely source of HCl. Let's summarize what we've talked about today. First, we talked about both inorganic and organic chlorides to illustrate how they differ, including how they move through a refinery. Then we identified the source of chlorides and how they often end up in crude oils. Then we discussed the various test methods used to quantify the two types of chlorides and the associated nuance. In particular, we spent a lot of time and talked about the D4929 test method. And lastly, we shared some of the experiences the industry has had about chlorides, including a case study, round robin, and some cautionary notes about results interpretation and assumptions. That's it for this episode. Thanks for watching, and I look forward to connecting again. If you would like further information about this topic or any others the CCQTA is working on, please refer to our website at CCQTA.com. If you have any feedback, please send it to secretary@CCQTA.com. Please check back regularly for new additions to our Lunch and Learn series and other videos.